Assalamualaikum and good day. So section 6.4 discusses operational properties of the Laplace transforms, and we can use these operational properties to solve problems in finding Laplace transforms and inverse Laplace transforms of given functions without having to resort to the basic definition of Laplace transforms. Section 6.4 has three subsections. The first one explains about the translation on the s-axis. The second one covers translation on the t-axis, and the third one touches on the derivatives of transforms. So we're going to go through them one by one. So let us now begin discussing 6.4.1 translation on the x-axis. The S translation theorem. If Laplace transform of f of t is equal to fs and a is any real number, then the Laplace transform of e to the power of at f of t is equal to f of s minus a. Now what does this theorem mean? It means that if we multiply f of t by e to the power of at and we want to get its Laplace transform, then the answer is not f of s, but instead the s now is replaced by s minus a. So that the Laplace transform of e to the power of at f of t is equals to f of s minus a. Now let us look at the graphs of f of s and f of s minus a. So suppose this is the graph of f of s, and this is the s-axis, and we note a point A on the s-axis where A is positive. So when you say f of s minus a, it simply means the graph of fs shifted by an amount of a unit along the s-axis. Or we say that a translation of fs occurs along the s-axis by an amount of a unit. So that's why we say this theorem as the S translation theorem. Okay, here's a quick proof of the theorem. Let's look back at the definition of the Laplace transform. Okay, Laplace transform f of t is equal to the integration from 0 to infinity e to the minus st f of t dt is equal to fs. Now we are interested to find the Laplace transform of e to the power of at f of t. Okay, where this e to the power of at f of t is replacing this f of t. Okay, so this is the proof. Laplace transform of e to the power of at f of t is equals to integration from 0 to infinity. Okay, e to the minus st. But now this f of t has been replaced by e to the power of at f of t and integrate with respect to t. Okay, the product of these two means you have to add the powers of the exponential function, resulting in e to the minus s minus a of t f of t for the integrand. And when you compare between these two, alright, the only difference is the s now has been replaced by s minus a. So if this integral is equals to fs, and definitely this integral will be equals to f of s minus a. Okay, so this is the proof for the S translation theorem. Laplace transform of e to the power of at f of t is equals to f of s minus a. In this table of Laplace transform, you can see the formula that relates to the S translation theorem found at row number 20. Okay, so the Laplace transform of e to the power of at f of t is equals to f of s minus a. Let us look at formula number 1. Okay, Laplace transform of 1 is equals to 1 over s. So this number 1 is the f of t. So what if this number 1 is multiplied by e to the power of at? That means what is the Laplace transform of e to the power of at? According to the S translation theorem, whenever the function f of t is multiplied by e to the power of at, the result of the Laplace transform will be expressed in terms of s minus a. So to get the Laplace transform of e to the at, which is actually 1 multiplied by e to the power of at, we simply use the result of the Laplace transform of 1, except that the s now been replaced by s minus a. Okay, so the Laplace transform of 1 is 1 over s. Therefore, the Laplace transform of e to the power of at is equals to 1 over s minus a. And this formula is found at row number 4. Let's try another one. Look at formula number 2. Laplace transform of t is equals to 1 over s squared. Let us multiply t by e to the power of at. So according to the formula of the S translation theorem, whenever the function t is multiplied by e to the at, to get its Laplace transform, we can use the result of the Laplace transform of t, which is 1 over s squared, but we need to replace the s by s minus a. Therefore, the Laplace transform of t e to the at is equals to 1 over s minus a squared. So this formula of Laplace transform can be found at row number 9. Laplace transform of t to the power of n is equals to n factorial divided by s to the power of n plus 1, row number 3. When we multiply this t to the power of n by e to the power of at, so we expect the result will be as follows. Use the result of number 3, except that the s now been replaced by s minus a. So the answer will be, for the Laplace transform of t to the power of n e to the power of at is n factorial divided by s minus a to the power of n plus 1. So the formula for this Laplace transform is found at row number 10. Laplace transform of sin kt is equal to k over s squared plus k squared, formula number 5. If we multiply sin kt by e to the power of at, so according to the S translation theorem, we use the result of the formula of the Laplace transform of sin kt, except that we need to replace the s by s minus a. So the answer for this Laplace transform e to the power of at sin kt is k over s minus a squared plus k squared. Okay, so this s has been replaced by s minus a, and the formula for this Laplace transform is found at row number 11. So as formula number 12, which is related to formula number 6, okay, we just have to replace the s by s minus a. And formula number 13 relates to formula number 7. Again, the s has now been replaced by s minus a. And formula number 14 relates to formula number 8. Okay, so the s has been replaced by s minus a for formula at row number 14. Okay, so these are the formulas that we have already covered that relates to the S translation theorem. So notice that formula number 4, 9 until 14, they are all functions f of t multiplied by e to the power of at. And notice that the result of the Laplace transform of f of t e to the power of at, they are all expressed in terms of s minus a. Okay, s minus a. Alright, so all of them are expressed in terms of s minus a. Now we are going to learn how to find the Laplace transform of some functions where we can apply the S translation theorem. So question number 1, find the Laplace transform of e to the negative 2t sine 4t. Okay, so how do we solve this question? So you search from the table of Laplace transform which formula from the table of Laplace transform matches the function given in this problem. So you found that this expression here matches formula at row number 11. Okay, formula number 11, Laplace transform of e to the power of at sine kt is equal to k over s minus a squared plus k squared. So what you have to do is to match this expression with the one given in the problem and determine the a and the k. When you compare between these two, we find out that the a is equals to negative 2, okay, and k is equals to 4. So simply apply the formula, substitute k by 4 and the a by negative 2, so the result will be 4 divided by s minus negative 2, which becomes s plus 2 squared plus k squared. 4 squared is 16. Okay, so this is the answer for the given question. Next question, what is the Laplace transform of e to the power of 3t multiplied by 2t minus 1 squared? Okay, so to get the result, of course, we need to square the given function, 2t minus 1. Alright, So there will be Laplace transform of e to the power of 3t multiplied by 2t minus 1 squared is equals to the Laplace transform of e to the power of 3t. Okay, now squaring this function, I'm using the formula a minus b squared. That will be a squared minus 2ab plus b squared. So it becomes 4t squared minus 4t plus 1. Next step is to multiply each of the term inside the bracket with the factor e to the power of 3t and apply linearity of the Laplace transform. We need to get the Laplace transform of three functions. The first one will be Laplace transform of 4t squared multiplied by e to the power of 3t minus the Laplace transform of 4t multiplied by e to the power of 3t plus the Laplace transform of 1 multiplied by e to the power of 3t. So there are three Laplace transforms that need to be evaluated. So you need to search from the table of Laplace transform which formula matches the ones stated in this line here. Okay, so for the first one, it seems that we need to apply formula number 10. Okay, Laplace transform of t to the power of n e to the power of at equals to n factorial divided by s minus a to the power of n plus 1. So to apply formula number 10, we have to find out what is the value of n and what is the value of a that's given in this part of the problem. So it seems that n is equal to 2 and a is equal to 3. And for this part here, we need to apply formula number 9. Laplace transform of t e to the power of at, okay, is equals to 1 over s minus a squared. A in this question is equal to 3, alright, and this function is multiplied by the constant 4, so 4 can be factored out, plus the Laplace transform of e to the power of 3t, this is formula number 4. Okay, Laplace transform of e to the at equals to 1 over s minus a. So what we have to do is to substitute a by the number 3. Now let us write down the result of the Laplace transforms of each of these. Okay, so for the first one, 4 multiplied by, okay, this is the constant 4 which can actually be factored. Transform of t squared e to the power of 3t based on formula number 10 is 2 factorial divided by s minus 3 to the power of 2 plus 1. Okay, so 4 times 2 factorial divided by s minus 3 cubed. Minus, okay, the Laplace transform of this function used from formula number 9. So it will be 4 times 1 which is 4 divided by s minus 3 squared. Plus, and for the last one, formula number 4, we substitute a by 3. So the answer will be 1 over s minus 3. So you can leave the answer in this form, or you can take the product of this and write it as 8. Okay, so 8 over s minus 3 cubed minus 4 over s minus 3 squared plus 1 over s minus 3. Next question number 3, Laplace transform of cos 7t divided by e to the power of 3 over 2. So firstly, we need to rewrite this as follows. Because so bring e to the power of 3 over 2 up, so that will give us e to the power of negative t over 2 cos 7t. Can look from the table of Laplace transform, find a formula that matches with the one given here, and it seems that it matches formula number 14. Okay, formula number 14, Laplace transform of e to the power of at cos kt. So comparing these two, notice that a is minus a half, a is negative a half, and k in this question is given by the number 7. Okay, so just substitute a by negative half and k by 7, so we get the result for the Laplace transform of this question is s minus a, s minus half, that gives s plus a half, divided by s plus a half squared minus 7 squared is 49. Okay, so this is the result for the Laplace transform of cos 7t divided by e to the power of half t. Let us learn inverse now, the inverse form of the S translation theorem. According to the S translation theorem, the Laplace transform of e to the power of at f of t is equals to f of s minus a. So this implies that the inverse Laplace transform of f of s minus a is equals to e to the power of at f of t. Okay, so the inverse of a function expressed in terms of s minus a is equals to the product of e to the power of at with f of t. So if we want to find the inverse Laplace transforms of rational functions by using the S translation theorem, we need to check the forms of the given rational functions. Okay, so firstly, check for the denominator. If the denominator of the rational function is an unfactorable quadratic polynomial, we need to rewrite the denominator by completing the square. Okay, so check for the denominator. Is it quadratic? And if it is quadratic, can that quadratic factor be factorized or not? If it cannot be factorized, then complete the square of the denominator. Okay, so for example, this is a quadratic factor, s squared plus bs plus c, and this quadratic factor cannot be factorized. So what's the formula to complete the square of this quadratic factor? So this is how it's done. Okay, now take note that b and c are constants. So s squared plus bs plus c. So firstly, you take the middle constant here, b, and consider half of it. So you write down s plus half of b, or s plus b over 2, and you square the whole thing here. Then add with the last term, which is c, and that c should subtract the square of b over 2, which is b squared over 4. Okay, so s squared plus bs plus c is equals to s plus b over 2 everything squared plus c minus b squared over 4. So this is the formula when you complete the square of the denominator, which is expressed in the form of s squared plus bs plus c. Second thing that you have to check is the translation s minus a. Does s minus a appears in the denominator or not? If yes, then you check also whether s minus a appear at the numerator. Now, if the translation s minus a does not appear in the numerator, then it is necessary to replace every s throughout the numerator by s minus a. Okay, so every s in the numerator should be replaced also by s minus a, followed by some fixing up and manipulation of the constants involved. Okay, so we'll explain these 2 points, points 1 and 2, by looking at some examples. So let us try one question first. Evaluate or find the inverse Laplace transform of s divided by s squared plus 8s plus 3. Now this is a rational function and the denominator is quadratic. If it is possible to factorize this quadratic factor, then we can find the inverse Laplace transform of the rational function by using partial fractions. However, this quadratic factor cannot be factorized, therefore we have to resort to the technique of completing the square of the denominator. So this is how it's done. Take the middle number, which is 8, and divide it by 2. So 8 divided by 2 is 4. So we write down s plus 4 everything squared, plus the last number, in this case the last number is plus 3, minus the square of 4, which is 16. Okay, so it becomes s plus 4 everything squared minus 13. Now you can check whether your work is right or wrong. Try and expand this and see whether your result is the same as the original factor or not. If they are the same, that means your work is correct. If they are not the same, it means that you have to complete the square of the denominator. Okay, now we are at this part. We need to find the inverse Laplace transform of s divided by s plus 4 squared minus 13. Now, according to the rule, if the denominator contains a translation in the form of s minus a, in this case a is negative 4, then the numerator must have the same form as minus a or s plus 4. But in this case, the numerator contains only s. There's no s plus 4 at the numerator. So what do we need to do? The procedure is as follows. You need to change this s into s plus 4 so that they are the same. Okay, the translation form at the denominator must also appear at the numerator. So if this is s plus 4, then this must also be s plus 4. But by doing so, we have added a new number 4, whereas the original factor at the numerator is only an s. So to get back s, we have to take away 4. So s plus 4 minus 4 gives back s. Okay, so these two are equivalent. So next step, we have to apply termwise division. First term, s plus 4 divided by the denominator minus the second term divided by the same denominator. So the inverse Laplace transform of s plus 4 divided by s plus 4 squared minus 13 minus, okay, follow the sign. If this is minus, you put minus. If this is plus, you put plus. So in this case, it is minus the inverse Laplace transform of 4 divided by s plus 4 squared minus 13. Okay, but by the linearity of the Laplace transform, since 4 is multiplied by 1, so we can take out the number 4 and leave 1 inside. So negative 4 inverse Laplace transform of 1 divided by s plus 4 squared minus 13. To get the inverse Laplace transform of each of these functions, we need to refer to the table of Laplace transform and find out which formula from the table that exactly match or closely match with the functions shown in this line here. Okay, so for the first part, it seems that this function matches the form given at formula number 14. Okay, s plus 4 divided by s plus 4 squared minus 13 matches with this form s minus a squared minus k squared. Okay, so when you compare between these two, we find out that a is equals to, s minus a is equals to negative 4. And the k squared is 13, that means k must be square root of 13. Okay, and for this inverse function, we find out that this expression here closely match with the form given at formula number 13. Okay, k divided by s minus a squared minus k squared, so a must be negative 4, s minus 4, so a is negative 4, minus k squared is 13, therefore k must be square root of 13. Now according to the rule, if there is a k squared at the denominator for formula number 13, a k must appear at the numerator, but unfortunately here we don't have a square root of 13 at the numerator, so we need to apply some manipulation to find the inverse of this Laplace transform of this function. Okay, so this is how we're going to do it. So you write down square root of 13 at the numerator and divide back by square root of 13. Okay, this part here we have learned in chapter or in section 6.2. Okay, so please refer to section 6.2 once again to find out how to get this form here. Okay, so we write down square root of 13, divide back by square root of 13 to get back the original function. And after this, we can start applying formulas 13 and formulas 14. So from formula number 14, the inverse of s minus a divided by s minus a squared minus k squared is e to the power of at cos kt. So just substitute a by the negative 4 and substitute k by square root of 13. So the answer will be, the answer for the inverse Laplace transform for the first function will be e to the minus 4t cos square root of 13t. Minus, for the second part, will be 4 over square root of 13. Now, the inverse of this function, we can apply formula number 13, e to the power of at, a is negative 4, so e to the power of negative 4t, sinh square root of sinh kt, k is square root of 13, so sinh square root of 13t. Okay, so this is the result for finding the inverse of the given rational function. Second question, find the inverse Laplace transform of 3s divided by s minus 6. Now this is a rational function and it is obvious that the denominator contains a translation in the form of s minus a where a is equal to 6. Okay, so if there is a translation in the form of s minus a or s minus 6 at the denominator, then according to the rule, the s that appear at the numerator must also be of the form s minus 6. Unfortunately, the s at the numerator here is not the same as s minus 6. So we need to manipulate this s, we need to change this into s minus 6. Okay, so we write, instead of 3 multiplied by s, now it becomes 3 multiplied by s minus 6. But by doing so, we have actually altered the original function, because when we expand this, we'll get 3s minus 18, whereas originally it is only 3s. So how to eliminate the negative 18? We have to add 18. Okay, because 3s minus 18 plus 18 gives back 3s. Alright, so whatever manipulation that we do here, you must make sure that you get back the same original function. Next step is to apply termwise division. Okay, so you take the first term divided by the denominator plus the second term divided by the same denominator. So we write down the inverse Laplace transform of 3 times s minus 6 divided by s minus 6 to the power 4 plus the inverse Laplace transform of 18 divided by s minus 6 to the power 4. So the step after this is to simplify the rational function before we evaluate the inverse Laplace transform. So for the first inverse, notice that we can factor the number 3, and when s minus 6 divided by s minus 6 to the power 4, we will be getting 1 divided by s minus 6 to the power 3. For the second inverse problem, we can factor the number 18, leave 1 inside, so 18 multiplied by the inverse Laplace transform of 1 over s minus 6 to the power 4. To find the inverse Laplace transform of each of these functions, we are going to refer to the table of Laplace transform, and it seems that formula number 10 closely match with what we are seeing here. Alright, now formula number 10, let's look at this part here. N factorial divided by s minus a to the power of n plus 1. Now compare this expression with the one shown here. So notice that you get the same form s minus a where a is equal to 6. And n plus 1 is 3, that means n must be 2. And according to formula number 10, there must be a 2 factorial written at the numerator. Unfortunately, there's no 2 factorial at the numerator, therefore we are going to do some manipulation after this. For the second part, okay, we can apply the same formula, s minus a, again a is equal to 6. Now n plus 1 is 4, that means n must be 3, and there must be a 3 factorial appearing at the numerator, but there's no 3 factorial now. We have to do some manipulation after this. Okay, so for the first inverse, a 2 factorial of the number 2 must appear at the numerator, so we write the number 2. But to get back 1, we have to divide back by 2, okay, because 2 divided by 2 gives back the number 1. And similarly for the second part here, we write down 3 factorial at the numerator. To get back the number 1, we divide back by 3 factorial. Now if you have forgotten this technique, please refer to section 6.2, where we have explained in detail how to manipulate the function given. Okay. Next step is to apply formula number 10. Okay, so for the first term, get 3 over 2 multiplied by t to the power of n. Now n is equal to 2, so add t squared, e to the power of 80, e to the power of 60. Okay, a is equal to 6. For the second part, now 18 divided by 6 is 3, and the inverse of this, using this formula, t to the power of 3 was n equal to 3, e to the power of 60. Okay, so the inverse Laplace transform of 3s divided by s minus 6 is equals to 3 over 2 t squared e to the power of 60 plus 3t cubed e to the power of 60. Now we are moving into 6.4.2, translation on the t-axis. This section starts by discussing a special type of function known as the unit step function. The unit step function is denoted by ut minus a. Now ut minus a is equals to 0 or 1. It is 0 for t larger than or equals to 0 less than a, and it is equals to 1 for t larger than or equals to a. Okay, so let us look at the graph of the unit step function. This is the t-axis, and let us plot a point A on the t-axis where a is larger than 0. According to the definition of the unit step function, within this interval, for t larger than or equals to 0 less than a, the function is equals to 0. Okay, so this is equal to 0. At the point when t equals to a, the function starts to jump up by 1 unit, and it remains at the number 1 for t larger than or equals to a. Okay, so ut minus a equals to 1 for t larger than or equals to a. So this is the definition of the unit step function. Now the number 0 can be regarded as a function that has been turned off, and the number 1 can be regarded as the function that has been turned on. Okay, so in engineering, for example, In a mechanical system, the external force can be turned off or turned on for a period after a period of time. And also, for example, we have a voltage impressed on a circuit. The voltage can be turned off or on after a period of time. The unit step function can also be known as the Heaviside function, named after the English polymath Oliver Heaviside. So if we use the term Heaviside function instead of the unit step function, then we have to use the notation h t minus a instead of u t minus a. For the unit step function, if we let a equals to 0, then ut minus a is equals to ut minus 0, that is ut. So what is ut equals to? Now this is the graph of the function ut. Based on the definition of the unit step function, at t equals to a, where a equals to 0, so at this point a equal to 0, the graph or the function starts to jump up by 1 unit, and it remains at the number 1 from t equals to 0 until infinity. In other words, ut is exactly equals to 1 for t larger than or equals to 0. Okay, so this is the value for the function ut, which is 1. Now the height of the unit step function can also be modified by multiplying it with a constant. Okay, let's look at this figure. Firstly, we have the function ut minus 2. It means that the function is equals to 0 from interval t larger than or equals to 0 less than 2, but then it starts to jump up by 1 unit for t larger than or equals to 2. So this is the function of ut minus 2. Now suppose we multiply the function ut minus 2 by the number 3. Okay, so 3 multiplied by ut minus 2. Remember, by definition, it is equal to 0 or 1, but this time 0 needs to be multiplied by 3 and 1 needs to be multiplied by 3. So 0 times 1 is 0, 1 times 3 is 3. So 3ut minus 2 is equal to 0 for t larger than or equal to 0 less than 2. Okay, so within this interval, the function is still 0, but for t larger than or equals to 2, the function starts to jump up by 3 units, and it remains at the number 3 for t larger than or equals to 2. What is the effect of multiplying a function f of t by the unit step function? Okay, so f of t multiplied by ut minus a. By definition of the unit step function, ut minus a is either 0 or 1 depending on the interval for the variable t. Okay, so when we take f of t multiplied by ut minus a, it means f of t multiplied by 0 for t larger than or equals to 0 less than a, or f of t multiplied by 1 for t larger than or equals to a. But f of t times 0 gives 0, and f of t multiplied by 1 gives f of t. So f of t ut minus a is equals to 0 for t larger than or equals to 0 less than a, and it is f of t for t larger than or equals to a. Okay, so let's say this is the graph for the function f of t. F of t can be any function. So what is the effect when we multiply this f of t by the unit step function according to what we have computed just now? From t larger than or equals to 0 less than a, the function f of t ut minus a has been turned off to 0. So this is exactly equals to 0. But for t larger than or equals to a, the function picks up by itself. So this is the function f of t. So originally the function looks like this. Now this portion of the graph has been turned off to 0. Okay, when we multiply f of t by ut minus a, whereas the remaining part of the graph remains the same as the original one, starting from t larger than or equals to a. So we say that when the function f of t is multiplied by ut minus a, the unit step function suppresses or turns off f of t from t larger than or equals to 0 less than a, but turns on or has no effect on the remaining part of f of t. The t translation of f of t. We know that the function f of t minus a is the function f of t shifted a units to the right. Now what if f of t minus a is multiplied by the unit step function? Now ut minus a is either 0 or 1. That means f of t minus a, ut minus a is either 0 for t larger than or equals to 0 less than a, or it is f of t minus a for t larger than or equals to a. Okay, so this is the graph. Within this interval, the function is equal to 0 for t larger than or equals to 0 less than a, but for t larger than or equals to a, you get the function f of t minus a. Now this function f of t minus a is actually the graph of f of t shifted a units to the right. So the translated or shifted function is also known as a time delayed function. So assuming that t is time, so this graph is 0 in the interval t larger than or equals to 0 less than a, while delaying the start of f of t to t equals to a. So the function does not operate within this interval 0 until a, but it starts to operate only after t equals to a. The t-translation theorem. The t-translation theorem deals with the Laplace transform of the delayed function f translated along the t-axis. So in the previous slide, we have already discussed about the delayed function f. Now we are interested to find out the Laplace transform of the function. So the Laplace transform of f of t minus a ut minus a by the t-translation theorem is equals to e to the negative as fs. Okay, where a is a positive number. But we know that fs is the same as the Laplace transform of f of t. So this theorem says that the Laplace transform of f of t minus a ut minus a can also be evaluated by finding the product of e to the minus as with the Laplace transform of f of t. If we let f of t minus a equals to 1, okay, then the Laplace transform of 1 multiplied by ut minus a, or the Laplace transform of ut minus a, is equals to e to the negative as Laplace transform of 1. But Laplace transform of 1 is 1 over s, and therefore the result is e to the negative as over s. Now let us look at the alternative form of the t-translation theorem. Now, so this is f of t, and we say f of t minus a is the function f of t shifted a units to the right. Let us rename this f of t minus a, let us call it as gt. Okay, so if f of t minus a is now named as gt, therefore f of t will be named as gt plus a. Okay, so gt plus a is the function gt shifted a units to the left. Alright, so f of t is the same as gt plus a, f of t minus a is the same as gt. So let's look back at the t-translation theorem. It says Laplace transform of f of t minus a ut minus a. Now we can change it into Laplace transform of gt, because f of t minus a is equals to gt is equals to e to the negative as Laplace transform of f of t. Now this f of t is replaced by gt plus a. So this is the alternative form of the t-translation theorem, and I will explain later when to use this formula or this operational property. This table of Laplace transform contains the t-translation theorem or the operational properties that we have just discussed. Look at row number 21. The Laplace transform of f of t minus a ut minus a is equals to e to the negative as fs. Okay, but we know that fs is the same as the Laplace transform of f of t. You can even look up here. Laplace transform of f of t is equals to fs. So whenever we want to find the Laplace transform of f of t minus a ut minus a, it is actually advisable to use this formula instead, because we can find the Laplace transform of f of t based on the technique that we have learned. The next formula is at row number 22. Laplace transform of the unit step function is equals to e to the negative as over s. And at row number 23, we see the formula for the Laplace transform of gt ut minus a, which is actually the alternative form for the t translation theorem. Okay, so the Laplace transform of gt ut minus a is given by e to the negative as Laplace transform of gt plus a. Okay, so formula at row number 21 is the t translation theorem, whereas formulas 22 and 23 are actually derived from formula number 21. Let us do some questions. Question number 1. What is the Laplace transform of ut minus 3? To get this Laplace transform, we can obtain the answer directly from formula number 22. Laplace transform of ut minus a is equals to e to the negative as over s. Okay, so apply formula number 22 where we can replace a by the number 3. ut minus a is equals to 3. So the answer is e to the power of negative 3s over s. Okay, so this is a simple question. Question number 2. Laplace transform of t minus 2 to the power of 4 ut minus 2. Now look at the given function. Here is a fourth degree polynomial function, or we can say it is a quartic function. And this fourth degree polynomial function is expressed in terms of t minus 2. Similar to the unit step function, also expressed in terms of t minus 2. If this is the case, then we can find the Laplace transform of this function by using formula number 21. Okay, so in formula number 21, the function f is expressed in terms of t minus a. The unit step function is also expressed in terms of t minus a. So these two match. Alright, where a is given by the number 2. And f of t minus a is t minus 2 to the power of 4. Okay, so f of t minus a is t minus 2 to the power of 4. Now since a is equal to 2, we can also say f of t minus a is equal to f of t minus 2. Now to get the Laplace transform of this function using formula number 21, we need to determine f of t. Now if f of t minus 2 is t minus 2 to the power of 4, so certainly f of t must be t to the power of 4. Okay, so this is the function t to the power of 4. T minus 2 to the power of 4 means this quartic function or this fourth degree polynomial function has been shifted 2 units to the right. Now let us apply formula number 21. Okay, where a has been taken by the number 2. So according to the formula, the Laplace transform of t minus 2 to the power of 4 ut minus 2 is equals to e to the negative as. Now a is 2, so you write down e to the power of negative 2s multiplied by the Laplace transform f of t. Now we have already determined f of t as t to the power of 4, so replace f of t by t to the power of 4 in this formula. So you write e to the negative 2s Laplace transform of t to the power of 4. Laplace transform of t to the power of 4 can be obtained by using formula number 3 from the table of Laplace transform, which is 4 factorial divided by s to the power of 5. So we say that the Laplace transform of t minus 2 to the power of 4 ut minus 2 is equals to 24 e to the power of negative 2s over s to the power of 5. Problem number 3, Laplace transform of e to the power of t minus 6 ut minus 6. Can we apply formula number 21 to get this Laplace transform? Yes. This is an exponential function expressed in terms of t minus 6, and the unit step function is also expressed in terms of t minus 6, similar to the form given in number 21. Okay, so it means that a must be equal to 6, and the f of t minus a is e to the power of t minus 6. Okay, so f of t minus a is equals to e to the power of t minus 6. But a, as we know, is 6. That means f of t minus a is the same as f of t minus 6. Now in the formula 21, we are required to determine f of t. So what is f of t based on this given function? If f of t minus 6 is e to the power of t minus 6, certainly f of t must be e to the power of t. Okay, this e to the power of t minus 6 is actually the function f of t shifted 6 units to the right. Okay, now we're going to apply formula number 21. Laplace transform of e to the power of t minus 6 ut minus 6, where a equal to 6 in formula number 21, is equals to e to the power of, okay, replace a by 6, e to the power of negative 6s times the Laplace transform of f of t, where f of t in this problem is found to be e to the power of t. Okay, so you replace f of t by e to the power of t. Now we know Laplace transform of e to the power of t is simply 1 over s minus 1 from formula number 4 in the table of Laplace transform. So the result for the Laplace transform of e to the power of t minus 6 ut minus 6 is equals to e to the negative 6s over s minus 1. Let's do number 4 now. Find the Laplace transform of t squared ut minus 1. Can we apply formula number 21? Notice that the unit step function is expressed in terms of t minus 1, but this quadratic function is not expressed in terms of t minus 1. Since both of them are not of the same form, then we cannot apply formula number 21. Instead, we are going to apply formula number 23. Okay, notice that in number 23, the unit step function is expressed in terms of t minus a, but the function g is not expressed in terms of t minus a. So whenever they are not of the same form, then we apply formula number 23. So these two are not of the same form. So we apply formula number 23 to get the result of the Laplace transform of this function. So firstly, we have to identify the value of a. A certainly must be equals to 1. And the gt certainly is t squared in this problem. Okay, so you write g of t is equal to t squared. Now, in this formula number 21, we are required to determine gt plus a. Now, we know that a in this question is 1. So, gt plus 1. Okay, gt plus a is gt plus 1. Now, if g of t is t squared, then g of t plus 1 certainly will be t plus 1 squared. Okay, simply replace t by t plus 1. We have to maintain the type of the given function. If this is quadratic, this is also quadratic. Okay, applying formula number 23, Laplace transform of t squared ut minus 1, where a is equals to 1, is given by e to the power of negative 1s, or e to the power of negative s, multiplied by the Laplace transform of gt plus a. Now we have already found gt plus a or gt plus 1 as t plus 1 squared. So replace gt plus a by t plus 1 squared in this formula. So we write e to the negative s Laplace transform of t plus 1 squared. Okay, so this is t plus 1 squared. Now to get the Laplace transform of t plus 1 squared, we know from earlier lesson, we need to square this function first. So we get e to the negative s Laplace transform of t squared plus 2t plus 1, and find the Laplace transform of each of these using the formula from the table of Laplace transform. Laplace transform of t squared is 2 over s cubed, transform of 2t is 2 over s squared, and transform of 1 is 1 over s. So the Laplace transform of t squared ut minus 1 is equals to e to the power of negative s multiplied by 2 over s cubed plus 2 over s squared plus 1 over s. Next question, what is the Laplace transform of sine t ut minus pi? Notice that we cannot apply formula number 21 because the unit step function is expressed in terms of t minus pi, but this sine function is not expressed in terms of t minus pi, so they are not of the same form. Therefore, we have to resort using formula number 23. To use formula number 23, we have to identify the value of the a in the problem given, so a must be pi, and g of t is sine t. Okay, so g of t is sine t, and the formula requires us to find gt plus a. Now a we know is pi. So if g of t is equal to sine t, therefore gt plus a or gt plus pi must be sine t plus pi. Because simply replace the t by t plus pi, keeping the same function sine. Okay, once we have determined the gt plus pi, which is sine t plus pi, we can start apply formula number 23. Okay, formula number 23, where a is equals to pi, is given by e to the negative pi s, Laplace transform of gt plus a, or Laplace transform of sine t plus pi. Laplace transform of sine t plus pi. Now, how to find the Laplace transform of sine t plus pi? We have to apply trigonometric identity for this function. You can refer to the table of trigonometric identity. So sine t plus pi is given by sine t cos pi plus cos t sin pi. But sine pi is 0, so the second term goes to 0, and cos pi we know is equals to negative 1. So this is the same as negative e to the negative pi s Laplace transform of sine t. Okay, so cos pi is negative 1, so we have factored the constant negative 1. Laplace transform of sine t from the table of Laplace transform is given by 1 over s squared plus 1, and so the final result, Laplace transform of sine t ut minus pi is equals to negative e to the negative pi s divided by s squared plus 1. It's time now to study the inverse form of the t translation theorem. Formula number 21. Laplace transform of f of t minus a ut minus a is equals to e to the power of negative a sfs. It means that the inverse Laplace transform of e to the negative a sfs is equals to f of t minus a ut minus a. Here is the procedure for finding the inverse Laplace transform of e to the negative a sfs. First step, we have to find the inverse Laplace transform of fs, which is definitely f of t. Okay, so firstly find f of t by finding the inverse Laplace transform of fs. And second step, replace f of t by f of t minus a, and then multiply f of t minus a by ut minus a. Okay, let's look at an example. First question, evaluate the inverse Laplace transform of e to the negative 4s over s plus 7. So we need to identify the a in this question, and we also need to identify f of s. Notice that e to the negative 4s over s plus 7 can be rewritten as e to the negative 4s multiplied by 1 over s plus 7. So in this case, the a must be equals to 4. Right, and the fs is 1 over s plus 7. So we have identified a, and we already have identified fs. Once we have identified the fs, we need to evaluate the inverse of fs to get f of t. So let's do our work. Okay, fs is 1 over s plus 7. So to get f of t, we are going to compute the inverse of Laplace transform of 1 over s plus 7, which can be easily obtained from formula number 4, and the answer is e to the power of negative 7t. Okay, so we are done with step number 1. The next step is to replace f of t by f of t minus a. So if f of t is e to the negative 7t, now a, remember, is equals to 4, then f of t minus 4 must be e to the power of negative 7 t minus 4. Okay, so t is replaced by t minus 4, and therefore in this answer also the t is to be replaced by t minus 4. So f of t minus 4 is equals to e to the power of negative 7 t minus 4. So now we can write the final result. Transfer the result over here. Okay, so we have already got the f of t minus 4. And this f of t minus 4 must be multiplied by the unit step function ut minus 4. So this is the final answer for the inverse Laplace transform of e to the negative 4s over s plus 7, which is e to the negative 7 times t minus 4 ut minus 4. Second question, what is the inverse Laplace transform of e to the power of negative 5s divided by s cubed? We are going to apply the inverse Laplace transform of formula number 21, where we have to identify the constant a and the fs. So let us rewrite the function. e to the negative 5s over s cubed can be rewritten as e to the power of negative 5s multiplied by 1 over s cubed. So it seems that a is equals to 5, and this is certainly the fs. Okay, so fs is equals to 1 over s cubed. Once we know the fs, we have to find the f of t. So let us do our work. Fs is equals to 1 over s cubed. Therefore, f of t has to be the inverse of the fs, which is the inverse of 1 over s cubed. Now, referring to the table of Laplace transform, formula number 3, the inverse Laplace transform of 1 over s cubed is equals to half t squared. Now, this is f of t, but for formula number 21, the inverse Laplace transform of e to the negative asfs is f of t minus a ut minus a. So we have to find out what f of t minus a is. Now, since a is equals to 5, then we need to find what is f of t minus 5. Given that f of t is half multiplied by t squared, therefore f of t minus 5 is equal to half multiplied by t minus 5 squared. Okay, simply replace the t by t minus 5. Okay, now after this has been done, we just have to put the answer using this formula and multiply by ut minus a. Okay, so transfer our result back into here. So this is the f of t minus a multiplied by ut minus a. Okay, so we conclude that the inverse Laplace transform of e to the negative 5s over s cubed is equals to half multiplied by t minus 5 squared ut minus 5. Question number 3, what is the inverse Laplace transform of s e to the negative 5s divided by s minus 2 squared plus 9? Okay, let us rewrite this function in the form of e to the power of negative pi s multiplied by s over s minus 2 squared plus 9. Okay, so it is obvious that a is equals to pi. Okay, and this has to be the fs. Okay, fs. So fs is equals to s over s minus 2 squared plus 9. Okay, let us determine the f of t. Okay, this is our work. Fs is s divided by s minus 2 squared plus 9. So f of t certainly has to be the inverse of fs, which is the inverse of s divided by s minus 2 squared plus 9. Alright, now referring to the lesson that we have learned in the s translation theorem, if the denominator contains a translation in the form of s minus 2, therefore the s at the numerator must be of the same form. So this s has to be changed into s minus 2. They must be of the same form. Okay, so we rewrite s as s minus 2, but if we have written s minus 2, that means we have already changed the original function s. So to get back the original function s, we have to add 2, because s minus 2 plus 2 gives back s. Next, we are going to apply term-wise division. The first term divided by the denominator plus the second term divided by the same denominator. So we are getting the inverse Laplace transform of s minus 2 divided by s minus 2 squared plus 9 plus the inverse Laplace transform of 2 divided by s minus 2 squared plus 9. Okay, so in this case, I have factored the number 2 and leave 1 inside. So after this, we are going to find the inverse Laplace transform of each of the functions shown in this line here. Okay, so for the first one, I think we can refer to formula number 12. Formula number 12, where a is equal to 2 and k is equal to 3. So the answer will be f of t is equal to e to the power of 2t cos 3t. And for this part here, we need to refer to formula number 11. If this is 9, then therefore there must be a number 3 up here. Then you have to divide by 3. So the answer will be 2 over 3 e to the power of 2t sine 3t. Okay, so a equal to 2 and k is equal to 3. So this is the f of t, but formula number 21 does not require f of t. What it requires instead is f of t minus a. So we need to change f of t into f of t minus pi, because a is equal to pi. So in other words, every t that appears in the function f of t must be changed or must be replaced by t minus pi. So e to the power of 2t now becomes e to the power of 2 multiplied by t minus pi. Okay, 2 multiplied by t, now it has to be 2 multiplied by t minus pi. Cos 3 multiplied by t, now it becomes cos 3 multiplied by t minus pi, plus 2/3 e to the power of 2 multiplied by t, so e to the power of 2 multiplied by t minus pi, sine 3 multiplied by t now becomes sine 3 multiplied by t minus pi. So this is the function f of t minus pi. Okay, so we are done with this part. The next step is to just multiply the whole thing by ut minus pi. Okay, so transfer our result back into here. So this is f of t minus pi, and all of this has to be multiplied by ut minus pi. So put the whole thing in a big bracket. Okay, so this is the solution for question number 3. So the inverse Laplace transform of se to the negative pi s divided by s minus 2 squared plus 9 is equals to e to the power of 2 times t minus pi cos 3 times t minus pi plus 2 over 3 e to the power of 2 times t minus pi sine 3 times t minus pi, and all of this multiplied by u t minus pi. Now we are at the last part of section 6.4. So 6.4.3, derivatives of a transform. In this section, we are going to discuss theorem on derivatives of transforms. If the Laplace transform of f of t is equals to fs and n is any positive integer, then according to the theorem, the Laplace transform of t to the power of n f of t is equals to negative 1 to the power of n, the nth derivative of fs with respect to s. Okay, so notice that this n is a positive integer. So if n is an odd number, the sign here is negative. If n is an even number, the sign here will be positive. So we need to differentiate f of s with respect to s n number of times. Now take note that fs is equals to the Laplace transform of f of t. It means that this formula can be rewritten as Laplace transform of t to the power of n f of t is equals to negative 1 to the power of n, the nth derivative of Laplace transform of f of t with respect to s. Okay, so these two are the same. Now we're going to try and evaluate the Laplace transform of t sine kt. We can use the theorem to find the Laplace transform of this function. Okay, so when we compare this expression with t sine kt, we find that n is equals to 1, t to the power of 1, t to the power of n, so n must be equals to 1, and the f of t is sine kt. So using the formula, it will become negative 1 to the power of 1 d ds, okay, because n is equals to 1, we differentiate the Laplace transform of f of t. In this case, f of t is sine kt, so we differentiate the Laplace transform of sine kt with respect to s only once, okay, due to the fact that n is equals to 1. Negative 1 to the power of 1 is negative, and d ds, Laplace transform of sine kt, we can get it from the table. It is k over s squared plus k squared. So what does this mean? It means that we need to differentiate this function with respect to s, where k is a constant. Since this is a quotient of function, let us apply the quotient rule of differentiation to differentiate this function with respect to s. So the quotient rule of differentiation, we are going to name this as the u and this is as the v. The formula for the derivative will be v u prime minus u v prime divided by v squared. Okay, so the negative sign still remains. So v u prime. So v is s squared plus k squared multiplied by derivative of k. So okay, differentiate this constant with respect to s. Certainly the answer is 0 minus u. Okay, u is k multiplied by v prime. So differentiate the denominator with respect to s. The answer is 2s. Divided by the square of the denominator, which is s squared plus k squared squared. Alright, now the first term goes to 0, and so the numerator is negative, negative becomes positive, 2ks divided by s squared plus k squared squared. So using the theorem, we are able to get the Laplace transform of t sine kt, and the answer is 2ks divided by s squared plus k squared squared. Let us refer to the table of Laplace transform and search for the formula on the derivatives of transforms that we have just discussed. The formula is found at row number 24. The Laplace transform of t to the power of n f of t is equals to negative 1 to the power of n, the nth derivative of fs with respect to s. Formula number 24. But we know that formula number 24 can be rewritten as Laplace transform of t to the power of n f of t is equals to negative 1 to the power of n, the nth derivative of the Laplace transform of f of t with respect to s. Okay, because these two are equal, fs is the same as the Laplace transform of f of t. We also solved a problem in the previous slide, and that is the Laplace transform of t sine kt, and you notice that the answer is placed in this table of Laplace transform. Look at formula number 15, Laplace transform of t sine kt, which we have solved, and the answer is 2ks divided by s squared plus k squared everything squared. Now using the same procedure, we can find the Laplace transform of t cos kt, where we replace n by the number 1 and f of t by cos kt, and using this formula number 24, we should be able to get this result, where the Laplace transform of t cos kt is s squared minus k squared divided by s squared plus k squared everything squared. We can also apply the same procedure to find Laplace transform of t sin kt and Laplace transform of t cos kt. Okay, so these are the functions that we can find its Laplace transform using formula number 24. Let us try and solve some problems. Question number 1. What is the Laplace transform of t sine 8t? Okay, so firstly we have to try and search from the table of Laplace transform any function that exactly matches with the function given in this problem. So it seems that the function given in the formula at row number 15, t sine kt, matches with the function given in this problem, t sine 8t. Okay, so that means k must be 8. So applying formula number 15, we just have to replace k by 8. So 2 times k times s, for this case will be 2 times 8 times s, divided by s squared plus k squared everything squared. For this problem, it will be s squared plus 8 squared everything squared. So the Laplace transform of t sine 8t is equals to 16s divided by s squared plus 64 everything squared. Second question, what is the Laplace transform of t cos 3t? So here it seems that t cos 3t matches with t cos kt given in the formula at row number 18. Okay, so comparing these two, k is equals to 3. Alright, now just substitute k by 3 in the formula. So s squared plus k squared. In this problem, it becomes s squared plus 3 squared. S squared minus k squared everything squared. For this problem, will be s squared minus 3 squared everything squared. So the Laplace transform of t cos 3t is equals to s squared plus 9 divided by s squared minus 9 everything squared. Third question, what is the inverse Laplace transform of 6s divided by s squared plus 4 everything squared? Okay, now search from the table of Laplace transform a function that exactly match or almost match with the given function. Okay, so it seems that formula number 15 has a form which almost match with the form given in this problem. Look at the denominator. The denominator for formula number 15 is given by s squared plus k squared everything squared. And for this problem, the denominator is given by s squared plus 4 everything squared. So they are similar. Therefore, k squared is identified to be equal to 4, and hence k must be 2. In formula number 15, the numerator must contain the number 2 times k times s. So for this problem here, if k is equals to 2, therefore the numerator must contain the number 2 times 2 times s. But it does not happen here. This function at the numerator is not 2 times 2 times s. And therefore we have to manipulate this function in order for us to be able to use formula number 15. Okay, so apply formula number 15, k equals to 2. Firstly, we factor the number 6, leaving s inside. And remember what we have to do is to change this s into 2 times 2 times s. Okay, so write down 2 times 2 times s. But by doing so, we have changed or we have altered the original function. So to get back the original function, since this is 4s, we need to divide by the number 4. Alright, because 4s divided by 4 gives back s. So what we are having now is 6 over 4 times the inverse Laplace transform of 4s divided by s squared plus 4 everything squared. Next step is to simplify or reduce 6 over 4 into 3 over 2. And to get the inverse Laplace transform of this function, we can now apply directly formula number 15. Okay, where k is equals to 2. Okay, 2 times k times s, 2 times 2 times s, divided by s squared plus 4 everything squared. Alright, so the answer is, for this inverse, it will be t sine 2t. Okay, t sine 2t. Therefore, the inverse Laplace transform of 6s divided by s squared plus 4 everything squared is given by 3 over 2 t sine 2t. Question number 4. What is the inverse Laplace transform of 2s squared plus 10 divided by s squared minus 5 everything squared? So it seems that we can apply formula number 18. Look at the denominator, they have the same form. Alright, the numerator almost have the same form. So we're going to do something to the numerator. When we notice that the number 2 is a common number between these two terms, so take out the number 2. So because 2s squared plus 10 is the same as 2 times s squared plus 5. Factor the number 2 from the numerator. So what we are getting is 2 times the inverse Laplace transform of s squared plus 5 divided by s squared minus 5 everything squared. Notice that this form of this function has a similar is similar to the one given at row number 18, s squared plus k squared, s squared plus 5, where k squared is 5, divided by s squared minus k squared everything squared, divided by s squared minus 5 everything squared. Okay, so the inverse Laplace transform of this function using formula number 18 is t cos square root of 5t, cos k is square root of 5, and multiply by 2. Okay, multiply by 2. So the inverse Laplace transform of 2s squared plus 10 divided by s squared minus 5 everything squared is equals to 2t cos square root of 5t. Finally, we have come to the end of section 6.4. Okay, the lesson is quite long, the material is quite heavy. Okay, so we have covered the S translation theorem, the T translation theorem, and the derivatives of transforms. So please understand the concepts and also the problem solving techniques related to the operational properties that have been discussed in this lesson. Okay, so thank you very much.